In complex analysis, we start out with complex differentiation, and it requires us to do a quick revision of complex numbers, remembering that the square root of -1 is j. Therefore, this denominator for a gives us 4j. And then in order for us to be able to write in the format that has been given to us, we have to get rid of 4j in the denominator, or just simply get rid of j in the denominator. So we multiply by j over j and then simplify, and we get the required result. Also, in B, in order for us to get rid of 2 plus 3j, we have to remember we multiply by the complex conjugate of the denominator. So that means we multiply by 2 plus 3j divided by 2 plus 3j. We just multiply by this, simplify, and we know that 2 plus 3j times 2 minus 3j will give you 4 plus 9, which is equal to 13. So your denominator is 13. Then make sure that to separate the terms so that we have x plus jy expression. For C, we know that we add or subtract the real terms together and the imaginary terms together. So we have j minus 5j. That gives us j plus 5j, which is 6j, as the imaginary term, and then minus 6, minus 4, minus 2, it gives us minus 6. So we've got negative 6 plus 6j as our answer. And then D, you could start out by removing the bracket in the numerator, 2 minus j all squared. That gives us 4 minus 4j plus 1. So that means 5 minus 4j in the numerator divided by 4 plus 4j. And then you multiply by the complex conjugate of the denominator, which is 4 minus 4j divided by 4 minus 4j. And don't forget to simplify and write in terms of x plus jy. And then continuing with our revision, solving for x. Now we're getting to one of the properties of complex numbers, where you equate the imaginary parts together and equate the real parts together for the equality of two complex numbers. So first things first, multiply out so that we simplify the left-hand side and then be able to equate the terms that are equal. So we've got 2xj minus 1. We had to recall that j squared is -1. And then we're multiplying j and 3xj. That gives us -3x. And then minus j times 2y equal to j 2y minus x plus 3 on the right-hand side. And then thereafter, equate the real terms together. So we've got -1 minus 3x equal to -x plus 3 as the first equation. And then take all the other terms that have got j and equate them together, noting that we don't have j in those. So you're just taking 2x and -2y and 2y on the right hand side. This gives us x equal to -2 and y equal to -1. And then we go to B, same story. The complex, or should I say the imaginary part, 7 is equal to x minus 2xy. And we note that on the right hand side we don't have the real term that does not have j, so therefore x plus 2 is equal to 0. So that gives us the value for x to be negative 2, and then we take this, substitute in the second equation, and get y equal to 9 divided by 4. C, I've not done it, so we note that first thing, what you could do, there are two ways, is to multiply by j over j on the right hand side and simplify, or take j to the other side. So you remove the brackets on the left hand side and then thereafter multiply by j and equate that to x minus 8j, and then remembering that we have to equate real terms together and imaginary terms together and solve. So it's up to you which method you use. So you can multiply by j over j on the right hand side only to get rid of that j in the denominator. Then for number 2, I chose to get rid of the power half, which represents the square root, by squaring both sides of this equation, and then I got e to power j pi equal to j squared. And then I take the left hand side because I remembered that I have to show that e to power j pi is equal to j squared. Then the left hand side, from Euler's equation, I wrote it as cos pi plus j sine pi. And then our calculators give us that cos pi is -1 and sine pi is equal to 0. So therefore, the answer for the left hand side is -1. And then we know that j squared is also equal to -1. So we've shown the expression to be true. And then number 3, z plus z bar times z minus z bar, and we're given that z is equal to 2 minus 3j. We need to recall that z bar represents the complex conjugate of z. So therefore that means if we've got z equal to 2 minus 3j, then that means z bar is 2 plus 3j. So what I did was to remember also that this is a difference of 2 squares. Hence, I got z squared minus z bar squared, and then substitute. In place of z bar, I wrote 2 plus 3j. Instead of z, I wrote 2 minus 3j. Remove the brackets, simplify. Please check whether this answer is correct. Number 4. Now we have to write the given function as u plus jv, noting that both u and v are functions of x and y. So what we remember is that z is equal to x plus jy. That's where we start. So first thing I did was to substitute in place of z, substitute x plus jy, simplify so that I get the real terms together and imaginary terms together, so that I can be able to multiply by the complex conjugate of the denominator. Please recall, the complex conjugate just requires you to change the sign of j. That's it. So because it's plus here, that means it will be minus there, and then you multiply out, and the numerator remains the same because we're just multiplying by 1, but the denominator, it will just be the real squared and the imaginary squared, noting that j times minus j gives us +1. hence it is in that format. And recall also that we are using U plus JV, so we have to separate the terms. We have to separate the terms so that we have x plus 2 over x plus 2 all squared plus y plus 3 all squared representing U, and then the next term representing J times V. B, we have here Z over Z bar plus 2, and then I substitute in place of Z, x plus JY, and then in place of Z bar, it's x minus JY, and I already did the rearrangement so that the real terms are together. So we've got x plus 2 minus jy in the denominator, multiply by the complex conjugate of the denominator, noting that the complex conjugate just requires me to change the sign of j. Multiplying out and then separate the terms, and please check whether this is correct. C, we've got z times e to the power j pi over 2. Substitute in place of z, x plus jy, and then in place of e to the power j pi over 2, we use Euler's formula. So it's cos pi over 2 plus j sine pi over 2. Recalling, or you can even use your calculator, cos pi over 2 is 0 and sine pi over 2 is 1. So the answer for this bracket is j. Then we just multiply out by j, and we get the real term now to be negative y and the imaginary term to be x. Then D, we're given f of z equal to z squared plus j 5z plus 3 minus j. All we need to do here, substitute x plus jy in place of z, and then simplify. Remove all brackets, simplify, and put the real terms together and the imaginary terms together. Please check whether everything is correct, especially the signs. Then we go to number 5. Now we're moving backwards. We're given in the previous exercise, number 4, we're given that for f of z in terms of z, and we're asked to write it in terms of x and y as u plus jv. Now we're given u plus jv. Take it backwards and write it in terms of z. First thing, remove the brackets so that we can be able to see which terms go together. And we recalled from the previous exercise that x plus jy all squared gives us those three terms, x squared plus j2xy minus y squared. And then take the other two terms and group them together, 2x and j2y. Then take out the common factor, and this gives us j z squared plus 2z. Then we go to B, given x squared minus y squared minus x plus j into 2 xy minus y. So same thing, remove the brackets first, and then again we get the similar situation where we have x squared plus j 2xy minus y squared. We group them together so that we know that they will form x plus jy all squared. Then the other two terms, we group them together, taking out the negative, so that we're left with x plus jy. Wherever there is x plus jy, we substitute z, and those three terms give us z squared. C, we've got 6 terms here, and again, first things first, remove the brackets. So I multiplied out by j in those three terms, and that's what I got. I got those three terms still. Okay. And then thereafter comes grouping. We have to, when we do the grouping, we have to look at terms that will have a common factor. And also the recalling the Euler's formula. Once you've got cos and j sine, then you know that you are going to have e to the power j depending on the argument of cos and sine. In this case, it's y. So we're looking to get e to the power jy. And e to the power jy is cos y plus j sine y. So whenever we do the grouping, we need to take the terms that when we take out the common factor, we are going to be left with cos y plus j sine y, as I did here. So I chose the first term and the fourth term, because common factor there is e to the power, it's x e to the power x and x e to the power x. And then secondly, the next one, e to the power x cos y and e to the power x sine y with j, put them together, and then the last two together. Take out the common factor, x e to the power x, and then we're left with cos y plus j sine y in those two. Then we go to the next one, take out e to the power x, we're left with cos y plus j sine y. But then comes the last one. Here we know we have to have cos, not j cos. So we take out j y e to the power x, so that we're left with cos in the first, cos y in the first term. But then the second term does not have j, instead it's got a negative sign. We need to remember -1 is equal to j squared. So all in all, this was just plus j squared y e to the power x sine y. So that means j can be taken out, leaving us with plus j, because j times j will give us j squared, which is equal to -1. And then in place of cos y plus j sine y, we substitute e to the power jy, and then recalling also the laws of exponents. If you've got the same base, you add the powers. So this is just e to the power x plus jy, e to the power x plus jy, e to the power x plus jy. And then the first term and the last term have a common factor that we can take out, so that we are left with x plus jy. Therefore, our answer is that one. And then we take e to the power z out, giving us z plus 1 all into e to the power z. Part of our recollection are those formulas, 1 over j equal to -j, because what you do is to multiply by j over j here, you'll get -j, and then -1 over j gives us j, because you still multiply by j over j, and your answer will be j. And then e to the power 0, we know any number to the power 0 gives us 1. And then Euler's formula, recalling that cos pi always gives us -1, but sin pi is 0. So the answer is -1. Whether we're adding or subtracting, sin pi is 0. And then cos pi over 2 is 0. And sin pi over 2 is 1. Hence, the answer is plus minus j. Same with cos 2n pi. and sine 2n pi. Whatever value of n, for n an integer, we always get 1 as the answer. And also, when the angle is n pi, that means we have negative 1 to the power n, because if it's cos 0, we get 1. Sine 0 is 1, is 0. And then when n is 1, we've got cos pi, which is negative 1, and still sine pi is 0. If n is equal to 2, we'll have cos 2 pi. Your calculator will give you 1, and sine 2 pi is 0. Cos 3 pi gives us negative 1, and sine 3 pi is 0 still. So we're always alternating between 1 and negative 1 depending on the value of n. And then we've got these last two, and all of these may be used also in Fourier series. Then we go to analytic functions, because we were just doing that revision of complex numbers leading us to analytic functions. So firstly, if a function has a derivative f prime of z that is valid at all points in the region R of the z plane, then we say f of z is an analytic function. And also any function that can be expressed in the power series format, then it's also an analytic function. All analytic functions that means functions that are differentiable in the region R of the z plane can be written or can be expressed in power series expansions. Also, for our syllabus, we're going to use the Cauchy-Riemann equations to prove that functions are analytic. So the Cauchy-Riemann equations require that the given f of z be written in the form u plus jv, because we have those two conditions that have to be satisfied: du over dx equal to dv over dy, and du over dy equal to the negative of dv over dx. If we're doing this differentiation, this is partial differentiation. We need to recall, when we're differentiating u with respect to x, we hold the other variables as constant. We treat them as constant. And then if we're differentiating with respect to y, we'll also hold the other variable as a constant. Please, let's recall that both conditions have to be met in order for a function to be analytic. Some functions, you will discover that one of these hold, but the other doesn't hold. Once one of the two does not hold, then that means the function is not analytic. Also, in order for us to move again, once we know that a function is analytic, then we can determine its derivative using those derivatives we got for the Cauchy-Riemann equations. We either use the first expression du over dx plus j dv over dx to find f prime of z. And please recall that immediately we do substitute du over dx and dv over dx, we need to simplify and then change the whole expression and write it in terms of z. Even we can use the second one where we do differentiation with respect to y, noting that now we start with dv over dy minus j times du over dy if we choose to use the second formula for the derivative. Once again, we're just recalling Euler's formula: e to the power jz equal to cos z plus j sine z, and then sine z is equal to 1 over 2j e to the power jz minus e to the power jz. These formulas can be proven directly from the Euler's formula. And we also get sine z. Please remember, sine z, the power of e has got j, but for sine there is no j. And also for sine z, we've got 1 over 2j, but for sine we just have 1 over 2. And this is the same as negative j sine jz. Cos and cosh are related in that format, in the sense that also the power of e does not have j, and cosh is equal to cos of jz. Let's do some examples using the Cauchy-Riemann equations to prove that our functions are analytic. And if we get a function that is analytic, then we are asked to find f prime of z. So the first function given to us is z bar plus j. We know z bar is x minus jy. Remember that we have to write the function in terms of u and v first. So substitute, simplify, putting the real parts together and the imaginary parts together, and please specify that your u is equal to x based on the expression you got for f of z, and v is 1 minus y. Note that we don't have j in the expression of v. V is multiplied by j, and v is a real function, so it does not have j. And then we do the derivatives as given by the Cauchy-Riemann equation. So we differentiate u with respect to x, that's 1, and u with respect to y. We don't have y there, so our answer is 0. Then we go to v. Differentiate v with respect to x. It does not have x, so it's 0. I'm hoping you realize that y, we hold it as, or treat it as, a constant when we're differentiating with respect to x for partial differentiation. Then dv over dy gives us negative 1. Then we need to check, are the conditions given by the Cauchy-Riemann equations met? Du over dx is supposed to be equal to dv over dy. So d over dx, which is equal to 1, is not equal to dv over dy, because there is d over dx, it's 1, and dv over dy is negative 1. They are not equal. Also, d over dx, so d over dy is 0, and it should be equal to the negative of dv over dx, which is true. The negative of 0 is 0 anyway. So the second one holds, but the first one doesn't hold. Therefore, the function is not analytic. Number 2. F of z has been given already in terms of u and v, and therefore we just specify what u is and what v is, and then find the derivatives. The derivative of u with respect to x is 3x squared, and then we've got 3y squared minus 3. And then v with respect to x is just 6xy. The other two terms don't have x, so we treat them as constants. And then u with respect to y, x cubed and minus 3x, we treat them as constants. We only differentiate the term that has got y, so giving us 6xy. And also the last term, v with respect to y, is 3y squared plus 3x squared minus 3. Now we go and check the Cauchy-Riemann equations. Firstly, du over dx must be equal to dv over dy. So those two are equal. Okay, the first equality holds. Then we go to the second one, du over dy must be equal to the negative of dv over dx, and in our case they are just equal. So therefore, again, the function is not analytic. Number 3, e to the power z plus j z bar. That's the function that we have been given. Firstly, change to x and y by substituting z and z bar, and then remembering that e to the power 2x plus j 2y is the same as e to the power 2x times e to the power j 2y. So the angle for cos and sine is 2y. So hence we have e to the power 2x cos 2y plus j e to the power 2x sine y. So I took out e to the power 2x. And then we have in the second term z bar is x minus jy, and then we multiply by j. Then we have jx plus y. And then we group together the terms that represent u, which do not have j, and the terms that represent v. And then we specify u are the first two terms, and v have the coefficient j, but we don't write j down. And then we do the differentiation, d over dx. In this term, we differentiate e to the power 2x, which is 2 e to the power 2x, and we take down cos 2y. And then the derivative of y with respect to x in this case is 0. Okay, and then because we're using partial differentiation, and then du over dy, now we hold e to the power 2x constant, and then differentiate cos 2y, which is negative 2 sine 2y plus 1. Then we go to v. Differentiate with respect to x first with 1 plus 2 e to the power 2x sine 2y. And then with respect to y, the first term is 0. Then we'll have 2 e to the power 2x cos 2y. Then we check whether the Cauchy-Riemann equations hold. D over dx must be equal to dv over dy. That equality holds. But then we come to du over dy, which is supposed to be the negative of dv over dx. The only negative term is the first one, but the second one is not. So that means that equality does not hold. Hence, again, number 3 is not analytic. Exercises that you can do to check whether the function is given analytic by making use of the Cauchy-Riemann equations. And if you discover any that is analytic, please don't forget to determine f prime of z and make sure that your f prime of z is in terms of z. So first things first, you would substitute z with x plus jy, and then multiply by the complex conjugate, which is x minus jy over x minus jy, and simplify. We do the same here. Substitute z first, simplify, and then if your term in the denominator still has j, you multiply by the complex conjugate and sort it out. And also number 3. Please work this out and see if you get everything.